Hello, this is Frazier Nyasulu again. And when I talk about lab this week, monoprotic titrations. Monoprotic meaning, in this case, that we're either removing an H plus or adding an H plus during the titration. So, in terms of the titrations we're doing today, let's pick up a pen here. Pointer options. Hydrochloric acid with sodium hydroxide, so acid base. Acetic acid with sodium hydroxide, weak acid, strong base. And then we'll kind of switch things around and take the base, sodium acetate. The acetate is a weak base, and we're going to titrate it with HCl. So we're performing those 3 titrations, but each group will perform 1 titration, and then we'll have the data logger set so that you can go from station to station observing the other titrations. We can do this because all the 3 titrations are actually done in exactly the same manner. In that way we save time. All right, so what are we looking for? As we do titrations, we want you to be able to specify the species in solution at various points in the titration and be able to describe the relative amounts. This is more than that, this is equal to that, and so on and so on. And then we want you to be able to write the equations that define the pH. The equation will either involve H plus, pH itself, or the OH minus. We want to be able to describe those at various points in the titration. Then, depending on what you put in the flask, we'll ask you to figure out to calculate the concentration of the important species. Then when I figure out the pH at the equivalence point here, and then think about what would be an appropriate indicator, acid-base indicator, if we were doing it that way. And if we look at the titration curve, and we'll talk about more of that later, want to determine Ka of the weak acid. And then for these 2 titrations, strong acid, strong base, and weak acid, strong base, want to compare them so we can decide or look at or conclude the effect of Ka. What does Ka, how does it affect the titration curve? And then we want to also get some idea of how far low you can take, you can force the titrations to go. Can you titrate every Ka, or does that be a strong acid, or is there a limit at which the thing doesn't titrate meaningfully? And so we'll look at that as well. And then we'll ask you to look at the acetic acid titration curve and look at that is acetic acid with sodium hydroxide, and look at sodium acetate with HCl, and think of the conjugate, the Ka-Kb thing. Look at the steep regions and compare them and make generalizations about how these affect each other. So that's all up today. Many of these things that you're gonna look at today, you'll be able to conclude by looking at your data. So you'll be constructing knowledge. All right, so there's our titration setup. So the famous data logger, a pH, right? And then the burette there, and this here is a drop counter. So of course you'll calibrate the pH in the normal way that you did last week. And then you'll also calibrate the drop counter. The drop counter counts drops, but we want to convert from drops to milliliters of whatever reagent is up here in the burette. So what you're going to do is run the burette, start with a certain non-volume, go 55 drops, read the volume, and look at the change of the change on the volume, and say, let's say 2.3 milliliters is equal to 55 drops. you'll feed that information into the data logger, and then as it counts the drops, it will automatically go from drops to milliliters. All right. So let's look at a titration curve. First, what is a titration curve? In our case, in this case, it's milliliters, pH on the y-axis versus volume or milliliters of the sodium hydroxide base for the first two titrations. Sodium hydroxide, HCl, sodium hydroxide, and acetic acid, sodium hydroxide. In the other case, it will be pH versus milliliters of the HCl. So that's a titration curve. We begin here, and you can see here these are they go drop by drops. You begin at certain pH. As you add the hydroxide, the pH changes slowly in this region, and then very steeply in this region. So that's a steep region, and then after that it kind of flattens out. So somewhere here we have actually converted all the initial acid, reacted all the initial acid. The question is, how do we find that point? We can surmise that it's somewhere here, but where exactly is it? Is it in the middle? Well, there's a way to find out where exactly this is, and it's called, let's plot the derivative. What's a derivative? Well, if I could find the slope between these 2 points, then the slope between the next 2 points, and then that one, and keep going out of slopes at various points, I can plot the slope between adjacent points, rise over run, yes, yeah, and then plot that versus volume. If I did that, what would I get? That's what it will look like. The regions where the derivative or the slope between adjacent points doesn't change too much, and then in the steep region of the titration curve, there is a big increase, and then it goes down again. And so the equivalence point happens to be whatever coordinates, x coordinate for that particular point is. So in a titration curve, you do the derivative plot in order to find the volume corresponding to the equivalence point. So in this case, the volume sorry, the volume is 20 milliliters. Go back here. Here, the slope between adjacent points increases very much, and so we're looking at the inflection point. That's what we're looking for. That's where the slope stops increasing and starts decreasing, and so that maximum there is the equivalence point. All right, so in a titration curve, what are we looking for? Well, we set important points, the initial pH, where we start, and we'll talk about why that's important in a bit here. The pH at halfway to the equivalence point, the volume corresponding to halfway to the equivalence point, that's a point where pH is equal to pKa. So this is sort of the standard way to figure out the Ka. You look at the point halfway, the pH corresponding to the point halfway to the end, to the equivalence point. And then, if you know the equivalence point volume, you can find the equivalence point pH. If I go back here, if I know the volume is exactly 20, then I can look up here. If I click, if this were a real thing in the data logger, I could then click on these points and find which volume is exactly 20, and then I could read the corresponding pH. So once you know the equivalence point volume, you go to the titration curve, identify that in the titration curve, read the corresponding pH. That's the pH at the equivalence point. All right, so let's look at some standard ones here and get the impression of things. So here is a case where we're titrating a really weak acid, so kind of really on the weaker side. What happens then? Well, what happens is you by being a weak acid, it sort of progressively starts. The initial pH is higher and higher on this scale here, and so it turns out if you're titrating with the same base, you'll end up in this region for all of them. So the higher you start, then the less well defined this steep region. There's no meat for, there's no steep region to assess when the weak acid is very weak. So weak acids can be untitratable. If you have a strong acid, the stronger the acid, the more titratable it is, because then when you start way down here in terms of pH. So if I'm exaggerating, the weaker the acid, the higher points you start, and then, yeah, maybe that's titratable. By the time you get here, it's like not going anywhere. So there it is. So you'll be able, after you've done it, get some idea of the limits of titratability. All right, how about if you start with a base? In this case, you guys are going to start going to titrate acetate with a strong acid, and so I called it hydronium ion in this case. This is a net reaction in this case. You start with that, this sodium is a spectator ion, and that's a net reaction. You're starting with a base, so the pH starts above 7-ish or there or higher than that, and then as you add acid, it goes down, right, all the way down. What happens, so if the equivalence point volume is somewhere here, let's say 4, what happens at the point where the volume is 2? You still have, at this particular point, pH is equal to pKa of the acid, because at this point you've converted half of the A minus into HA, and you have equal moles or equal concentrations of the weak acid and the base. And so if you apply the Henderson-Hasselbalch equation, pH is equal to pKa, not pKb, but pKa of the acid. In this particular case, the acid is whatever HA is. All right, so that's what you're gonna do in lab in terms of some experimental things. Let me go back to the first, the figure, in fact, the only figure in this case. What are we gonna do? Well, we are going to put down here 5.00 milliliters of whatever it is, the acid or the base. So we're going to use an autopipetter, HCl, 5 milliliters, so 1 ml 5 times. And then we're going to titrate this with 0.200 molar base for the first 2 cases. Where do we expect the equivalence point? At the equivalence point, we've just added just enough of the base to react with the acid. So let's see here. How many moles is this? I mean, okay, so first of all, it's 5 milliliters of 0.2. Can't write very nicely with this. 0.2 molar. So what you have is, you have 1 millimole. 1 times 10 to the minus 3 moles of acid. Down here, this is a 1-to-1 reaction. So how many milliliters do we need to add in order to get to the equivalence point? It's quite easy to figure out that you need 5 milliliters as well. After all, these are the same concentrations, right? 0.2, 0.2. So you're then expecting equivalence points to occur at around 5 milliliters when and if they're present. So our expectation is then that if I write pH versus milliliters, And if 5 occurs here, if this is 5, then what do I expect? I expect then around 5 to get the steep region and flattening thereafter. Suppose this is HA. Let me generalize it as HA. What's happening in the initial pH? What's happening there? Well, it's a weak acid, and so it's doing its normal ionization. And so you can write a Ka expression in the normal way. Ka is equal to H plus times A minus over HA. Talking concentrations here, obviously. Now, if I'm adding base, then as I add, when I get to here, some of the HA is going to A minus. So I then have a mixture with known values of HA and A minus. So for this region here, when I use the Henderson-Hasselbalch equation, pH is equal to pKa plus log A minus over, you know the story. And so halfway here, the HA and the A minus have the same concentration. So that's why at this point, pH is equal to pKa, because the log term vanishes. Good. At the equivalence point, if we're titrating HA, we've converted all of the HA to A minus. So, wow. If it's A minus, and A minus is weak base, I expect the pH to be basic. Can I calculate it? And so you have that exercise as part of your pre-lab. So you're going to write a hydrolysis reaction, and you're going to use a Kb expression to do this calculation. So weak acids titrated with a strong base. The equivalence point can be expected to be on the basic side. And so if I go all the way here, here, there's a Kb expression, right? Because in this case, you'll be writing A minus hydrolyzing, so you'll be creating OH minus, and then you can solve that equation in the regular way. What you'll find here is the OH, and then you can convert to H plus. All right, now if you are, let's see here, if you're titrating a base, A minus with this, then when you get here, you've converted all the A minus to HA. HA is a weak acid, so it's gonna do its acid ionization. So I expect the equivalence point to be acidic. And yes, you use the regular Ka expression that you've done many times, so that for X is the hydronium concentration, and from that predict the appropriate pH. So in this lab, we'll ask you to look at the experimental pH and then calculate a theoretical pH at the equivalence point. All right, then go back to the previous slide here. All right, so after the equivalence point here, we're still adding hydroxide in this particular titration curve. So the pH over here is just simply controlled. My apologies. It's simply controlled by the excess hydroxide. Titration curves. So what you will find generally is that if you look at these, the system begins to fail at around 10 to the minus 10 when Ka is less than 10 to the minus 10. Then the acid doesn't titrate. You're starting way too high here so that you don't get a steep region. Similarly for the base, if Kb is less than 10 to the minus 10, then the base doesn't titrate when you titrate it with a strong acid, that's HCl. That is, there isn't much room in this tip region to be able to meaningfully identify the equivalence point. So, that's the lab this week. Again, you do one titration and work through to the other titrations, so don't turn off the data loggers. And then the number of questions at the back, you want to work through those in class before you leave, so make sure that you're done all of those, because you'll need the support of your wonderful classmates, smart classmates. And so as we learn better in a cooperative fashion, and so we help each other and we explain things to each other, that kind of thing. So stay in the lab until you're done with the post-lab questions, or you may leave if time runs out. Have a great lab. Bye-bye.